do a little brief introduction, go over what's going to happen. So the lecture will be happening pretty much straight away, but keep in mind we will be available to answer your questions at the end of the talk, so you can think of really good questions throughout. And you can leave them as comment in the chat section on YouTube, or our members here can raise their hands or leave a message, and we can get on with the questions. So today we have Professor Axel Hagermann from, not from Sweden, but he is currently in Sweden with us to talk about an icy topic. I won't go into more details. I'll let you talk about it much more eloquently. So thank you for being here, and we can get started. Oh, brilliant.
Okay, thank you very much, Laura. I'll now try to share my screen and do my thing, and let's see how that works out. Okay. Can everybody see my screen? Yeah?
Yeah, it's visible.
Okay, excellent. Good. Well, thank you for inviting me. I'm going to talk about a topic that we do research on here in Kiruna at the University of Luleå, and formerly at Stirling University. But in fact, this topic covers several years of research that we've been doing. And what we do is basically something that is called like laboratory astronomy. So we do experiments on Earth, complemented by spacecraft data, but I'll tell you more about that. I should now, yeah, that works, okay. So, and what we do is we do research on ices. Now, ices, as you can tell by the little asterisk, actually, to us is not just water ice, it's anything that is volatile and frozen, so anything that basically is present in the outer solar system. Ices are, however, much more widespread in the solar system. You can find ices on Earth, Mars, the Moon, very, very common in the outer solar system, as I said. Ices are very important because they help control the planet's climate. If you think of what's happening on Mars or on Earth, they can turn into comets once they approach the sun. They help provide an environment supportive of life. That is quite important on Earth, as well as possibly farther out in the solar system. However, ices are not that well understood these days. So, I mean, we still know very little about, for instance, some landforms on Mars. How do they come about? What is happening on Mars? We don't entirely understand comets yet, despite two major missions by the European Space Agency and several other agencies as well. And for instance, one of the things we don't quite understand is how they can be hard and soft at the same time. We don't quite know entirely what makes asteroids stick together, because there are some asteroids that rotate so fast that technically they would be torn apart. So, I mean, ices can play a role in all these processes. So, what we do actually, we simulate these icy conditions. For example, on Mars, we create Mars conditions, we create the conditions on comets or asteroids. We can basically also just simulate a random cold place on Earth. And in fact, Kiruna actually itself, it can be quite cold. A couple of weeks ago, we had minus 33 degrees outside. So, we then examine ice behavior on scales of centimeters to decimeters. That's a very unusual scale in science, because most of the objects we look at are many, many kilometers in size, and most of the processes that physicists investigate are much, much smaller. They're on molecular scales. And our research is used to underpin theoretical models, to explain spacecraft data. And basically, we're trying to bridge the gap between physics, that means the micro scale of the actual physical processes and physical entities that are much, much smaller, and the macro scale, so the planetary scale observations, that means astronomy, space missions, and so on. So how do we create these planetary environments in the lab? Well, we've got a vacuum chamber. Obviously, space is mostly void, so we've got this fancy vacuum chamber. with a very, very good temperature control. It is cooled with liquid nitrogen. That's why you can see this little Dalek-like tank in front. And we're basically cooling the interior of this vacuum chamber with a cold plate to temperatures that can be as low as minus 150 degrees Celsius. We've got a CO2 line so that we can actually add a bit of Mars atmosphere in our vacuum chamber if you want to simulate Mars. And then we can also shine an artificial sun on it. This is a solar simulator, creates instant sunburn if you look into the beam, so also quite fancy. And that's basically what we use to simulate these space conditions. I've shown you the key equipment, so the environmental chamber, the solar simulator. We've got lots of freezers as well, because obviously we need to store samples if we do these experiments in cold conditions. We use loads of liquid nitrogen. However, we've got other key suppliers as well that are quite important. So we've got UV protection, obviously, because we're using the artificial sun. And one of my former PhD students provided this fancy UV protection here that you can see. Other key suppliers, for instance, are IKEA. Then we've got B&Q, for instance, for this said UV protection. We buy flexi tubs, a mixing tray. When we were still working in Milton Keynes at the European University, one of our suppliers was the indoor ski center in Milton Keynes, because, as you may know, in southeast England, you don't really get snow that often. And if you do get it, it usually means the roads are gridlocked and people panic. So what I'm going to show you now is how our research is related to some objects in the solar system. I mean, just to give you an idea of where we are. I mean, we are here, Earth. And we're going to start here. So we're going to start not that far out from Earth in the solar system. And I'll show you some of the research that we've done in relation to Mars. So this is basically a trajectory we're taking today, or tonight rather. And we're going to look at Mars polar caps. And we're looking at ices on Mars on the polar caps. The polar caps are not like Earth's polar caps in the sense that you don't only have water ice, you also have carbon dioxide ice on the Martian surface. Both of Mars polar caps are seasonally covered with carbon dioxide ice. However, on the northern polar caps, the carbon dioxide ice evaporates during the summer season, and then you've got a water ice base underneath. On the solar polar cap, we've basically got a perennial and a seasonal dioxide ice cap. And ices are linked to some of the most active geological features we can see on Mars' surface, and you can see enigmatic landforms, you can see dark deposits, you can see permafrost features on Mars. So basically, there's periglacial activity going on. And what is quite interesting is that we are used to water ice on Earth, and on Earth we are climatically, in terms of the pressure and the temperature, very close to the triple point of water. That means we can have water as liquid, as solid, and a gas. However, on Mars, the atmospheric pressure is so low that carbon dioxide ice you can only have either as a solid or and water equally you can only have as a solid or as a gas, or vapor rather. So moving on, some of these landforms have been dubbed spiders. Spiders on Mars. If you're familiar with the pop music from the 1970s, that will ring a bell. They tend to have more than 8 legs on Mars, though, and they were introduced by a camera team of one of NASA's earlier Mars missions, and these are negative features. That means the things you see in these pictures, they're actually troughs, they're depressions, and they occur in groups. So you've got these groups of these spiders here, and these central depressions are usually like 50 meters in diameter, and then the entire thing, including all these troughs, are usually a few hundreds of meters in diameter. And the question is, well, we don't have anything like that on Earth. How do these features form? And because they only occur in the near polar regions at high latitudes, in a region called the cryptic region. Cryptic because there were so many strange landforms that people got really, really thoroughly puzzled. We only see these features near the poles. That means basically that people immediately deduce that this has to have something to do with carbon dioxide ice. And some mechanisms have been proposed by people. There were also some models calculated The idea behind this is that carbon dioxide ice is mainly transparent to most wavelengths of sunlight that impinges on these ice sheets. That means basically that most of the solar light can penetrate the carbon dioxide ice, and consequently, it is not the surface of the ice that gets warmest, but whatever is underneath. And that means you can actually have, as shown in this cartoon on the right, you can have the solar flux impinging on the surface. It penetrates most of the carbon dioxide ice sheet, and is absorbed by the regolith underneath. Regolith is a fancy word for soil. And it then basically warms up the soil. Because there's carbon dioxide on top of the soil, the carbon dioxide then sublimates, and that means you've got gas being generated between the soil and the ice sheet, and the gas pressure can get so high that the ice sheet bends upwards and at some point cracks, and then all the gas has to emerge into the atmosphere. Now, as the gas emerges, it of course takes some of the loose soil, some of the small grains with it. They get entrained in the flow of the gas, and they get ejected in this process. So that is the hypothesis how these things form, and so some of these processes have been modeled before. However, it's very, very difficult to create these conditions in the lab, and this is basically, this process is driven by what is called the solid state greenhouse effect. It's very similar to what we see on Earth, and the effect that is basically messing up our climate right now. We've got solar radiation impinging on the ice. Some of the radiation is reflected straight away, some of it is absorbed and then is re-radiated as infrared. But we've got some sunlight penetrating through the ice layer, and they either then gets absorbed in some absorbing layer or by dark particles embedded in the ice. And of course, you've got some radiation also being absorbed in the ice. But whenever this radiation gets absorbed by these dark layers or particles, then that can result potentially in the sublimation of the ice surrounding this particle. And that means immediately, if it's a closed system, that the pressure has to build up within the ice. That is something we can't get on Earth, because on Earth, obviously, if we've got water is not that transparent to solar radiation, and even if we have this happening, what happens because of the atmospheric conditions we've got, the water melts, and so we can't have this massive pressure buildup on Earth. Now, this is what our experiments look like. I want to show you an example of how we tackle this solid state greenhouse effect and these spider formations on Mars in our laboratory. Now, what you see here is a little artificial Martian ice sheet, or Martian, polar cap, if you will, that we've made. This is a block of carbon dioxide ice, and on the scale here, to give you an idea, I mean, this is an M6 bolt. So the whole thing is about like 12 centimeters in diameter. It's about 12 centimeters high. This is a standard cable with a temperature sensor. And this is sitting inside our vacuum chamber at temperatures of roughly minus 120 degrees Celsius. We've got a Martian pressure in here, so approximately 6 millibars. And what we've done with this artificial ice sheet is that what you can't see here, we've embedded a little patch of absorbing material, namely Martian analog material. That means we've got some artificial Martian dust because we don't have any real dust from Mars. And we put that inside this sample and then sealed it again by refreezing this carbon dioxide ice block. So you can actually see something like a little seam here that indicates in the middle of the ice block, that indicates that basically there is something in between there. So in the center of this thing, there's a patch of dust, of red Martian, or artificial Martian dust. And if you now take a look at what's happening in the little red box on this video, you'll see something happening, because we're now shining the sun on it. The sun is coming from above. That's why you've got this shadow being created. And we're now running this as a time-lapse video. So you can see that the sun shines at it. Some of the frost obviously disappears, sublimate as well. And keep an eye on what's happening in the red box. You will see a little black spot appearing on the ice block. There we go. And then you've got this little black patch right underneath that black spot at the bottom. And you can see this thing growing. You can see actually there's more and more there's a little apron of dark stuff forming on this in this location. I'll display this again. So this is approximately, I think, 8 to 10 hours. That's how long it takes. So the ice melts, and at some point, the gas pressure within the ice gets so high that the gas finds its way out at the bottom left inside that red square. There you go. There's a little apron forming at the bottom where the gas gets ejected, and it's deposited there. So this was the first actually experimental simulation of this gas ejection process in Martian spiders. And we found that this is actually highly sensitive to variations in pressure and temperature, because obviously you are very, very close to the equilibrium point in terms of temperature and pressure, and inside that ice block, if you then irradiate this ice block, this sort of radiation. So there we go. I mean, we've in a way modeled a Martian process. We've in a way simulated a Martian process on Earth. We actually published this a couple of years ago. It was the first simulation of this process in a terrestrial environment. So we're now moving on. Since I'm talking about ices and dust, now comets were thought to be mainly ice with a little dust. That picture is changing. And we've had a mission to a comet very recently. That was the ESA Rosetta mission to comet 67P, Churyumov-Gerasimenko. I'll just call it 67P henceforth because it's easier. And of course, we've also got all the objects outside in the solar system, the Kuiper Belt objects, trans-Neptunian objects, which are thought to be mainly made of ice with some other gunk mixed in. So I just call them comet-like objects for the purposes of this talk. Now, what are comets? Given that I'm giving this talk to Astronomy Society, I don't think I should have to explain it, but nevertheless, well, we know that comets' orbits are more eccentric than those of other bodies in the solar system. And that tells us they are somewhat different from all the other stuff that is moving around in the solar system. And there are several classifications of these types of comets. One of them is by orbital period. We've got the short period comets with, obviously periods that are short, namely less than 200 years. And their orbits are not too much inclined with regard to the ecliptic plane. And then we've got the long period comets with the highly eccentric orbits. And their periods can be thousands of years, and their orbits basically are randomly distributed in space. Now, what we think is that possibly the long period comets actually have more of a, offer us more clues into the very early pristine conditions in the solar system. Now, we describe comets, as, when I refer to comets, I usually refer to the nucleus, which is basically the solid bit of the comet, as a core of ices and dust that is orbiting the sun. And then we've got all the other stuff that goes on as the nucleus approaches the sun, namely the ice is sublimate, and the nucleus then forms a coma, and the solar wind then takes the gas and the dust with it, and as a result, we've got a dust tail and an iron tail. And that's actually the comet we know. So what we call comet is the actual phenomenon that we see in the sky. But unfortunately, when I say comet, I actually mean the nucleus. So I mean, I need to apologize for that inconsistency when I talk about comets. Why are comets interesting? I mean, what makes us so so keen on observing them? They basically are thought to resemble cosmic freezers. That means they have formed a long distance away from the sun. That means they must have formed in a very cold environment because there is not much solar energy there. And then they particularly when you look at the long period comets, they must have spent most of the time since their formation in that very cold region. That means they haven't undergone much processing. So we think that comets are, somewhat akin to cosmic freezers. They enable us to look at the early youth of our solar system. So to look at conditions more than 4.5 billion years ago. Now, what do we know, and what does it mean? I mean, we're now, I'm just showing a few slides trying to follow the scientific method strictly. That means I'll give you some information, some observations, and then tell you, okay, this is how this has been interpreted. Okay, so we've seen the gas emission. We know that the nucleus forms in a coma, tails. So we see that happening. So we know that comets must consist of ice and dust, even without any spectrometers or spacecraft or anything. We also know that the dust can form very fluffy conglomerates. What we also see, and we were quite, or people, because I was in school then when the Giotto mission happened in the 1980s, we also see that comets are dark. Up until that point, people actually thought that, oh yeah, well, comets must be very icy. Surely they're fairly white. They're sort of snowballs, dirty snowballs, something like that. It then appeared that comets seem to be a lot darker than that. So when the ESA Giotto mission observed Comet Halley, they found that the albedo of this comet was quite low. It was almost as dark as coal. Albedo was like, I think, 4% or something, very, very dark. So at that point, that was interpreted because all the outgassing was seen, this is a dust mantle, and inside there must be lots of ice. This picture is also changing these days. From the Rosetta mission, we're now deducing that actually, the comet that Rosetta visited was not that icy at all. I mean, there was a lot of other components as well that were visible. So what we also see is that comet nuclei break up quite easily. There was this event when the comet Shoemaker-Levy 9 got very close to Jupiter and just broke up in Jupiter's gravity field. And then we had this pearl string of fragments, of comet fragments, that then orbited the sun on the same trajectory. From the fact that this thing broke up just because of Jupiter's gravity field, people deduced that, so comets must have very low cohesion, they must be soft. So there's another piece of evidence that actually showed us that comets must be soft. So it was quite interesting that the comets are so different, and we had to take a closer look. And what I'm going to show you now to get a break is this really, really interesting ESA video. And you can actually find these on YouTube as well as on the ESA website. And there is a complete and much, much better, much longer version of this. And if you follow this little animation, you will also find that all the events depicted here are historically very, very accurate. So, I mean, I'd like to invite you to pay attention to all the historical accuracies in here.
Over 10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P Churyumov-Gerasimenko. After 3 months investigating the comet from orbit, it was time to send Philae to its surface. A long night of final preparations lay ahead of them. Finally, the moment everyone had been waiting for arrived. As the world held its breath, Rosetta moved into the exact position needed to make sure Philae would reach the landing site that scientists on Earth had picked earlier in the mission. Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away. It would take 7 hours to reach the surface, but Philae wanted to get started on his measurements right away. He could soon see the surface in incredible detail, and the moment he had been dreaming of had finally arrived. He had reached the surface of the comet. But all was not right. His harpoons did not fire. Philae realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again. However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure to send all the data he had collected back to Rosetta. As the sun set over Philae's new home, he fell into a deep sleep, safe in the knowledge that he did his main job well and that his family of comet-chasing heroes would be proud of his achievement. Who knows? Perhaps one day enough sunlight would fall on his new landing site and wake him up so that he could carry on investigating this incredible world. And so, as the comet moved over closer to the sun, Rosetta prepared for the next part of her exciting adventure.
Right, as I said, you can get a full 20-minute version describing the whole mission from beginning to end on YouTube or on the ESA website. It is very instructive and, as I said, historically accurate. So to give you an idea of the Rosetta spacecraft, this is what real Rosetta looks like. It had lots of, the whole suite of remote sensing instruments on it, spectrometers, all the wavelengths. It had a radar experiment to sound the core, and so on. And this little thing on the side is the Philae Lander, and the wingspan of the Rosetta spacecraft was, I think, equivalent to an Airbus A340. So a massive thing. And this is Rosetta in real life, doing the commissioning tests on Earth. And to give you an idea of what the size is like, Rosetta was on the side here. So Rosetta also saw that the gravity of, or it probed the gravity field of the comet nucleus, and actually it found that it must be very, very porous because the density of the whole thing was quite low. So we've got another piece of evidence. And just to conclude with this whole, collecting evidence to gather information about something, scientific method, in order to deduce how large the Rosetta spacecraft is, you can compare it to a random reference object, which is located here. We know the size of the reference object, which is 178 centimeters. So we can conclude that Rosetta spacecraft is about 2 by 2 by 2 meters. Now the Philae Lander was attached to the side, and actually you could see it in the little video. Actually, it was then released by Rosetta to land on the comet. It also had a suite of instruments that were actually designed to investigate what this enigmatic frozen material would actually look like. It was supposed to sample something that is left over from the early days of the solar system. It had a drill to collect a sample, and various spectrometers, mass spectrometers, and so on to actually investigate this material. It also had ice screws in case it landed on somewhere on a place that was really hard, so it actually could screw itself into the surface. The famous harpoons that you saw in the cartoon that didn't fire were supposed to hold it to the surface as well, because there could be a rapid outgassing event that would then send it off into space again, and so on. But what this thing also had was this little self-propelling hammer. It basically looks like a stick with a Coke can attached, and that was supposed to be deployed just a few feet away from the Rosetta Lander, and then hammer itself into the surface using a cunning mechanical design that is equivalent to a mechanical diode. So things, as you could see in the video, did not quite go as planned. The taxpayer, however, was served quite well, because the taxpayer got 3 landings for the price of 1. Because the Philae Lander then bounced off the surface because these harpoons didn't fire. There was another failure of a cold gas system that was supposed to hold it to the surface. That didn't work either. And at some point, we were quite worried that actually it would disappear into space again, because the gravity field of this, of a comet nucleus is not huge. So this whole actually journey until it hit something and then bounced off and hit something again, that took quite a while. So we saw Philae bounce off the surface. Now all of a sudden, hang on a minute, but didn't Shoemaker-Levy 9 suggest that comets must be soft? So this suggests that comets must be hard. Otherwise, the Philae Lander wouldn't have bounced off the surface. So this is one of the contradictions that we then actually that began to unravel as the Rosetta mission progressed. Now, we also had this hammer on board, the self-propelling hammer that I talked about. It was, led by the University of Münster and DLR Berlin. Was built partly by the Space Research Center in Warsaw, so it was a massive international effort. And this thing was supposed to be deployed a bit away and then hammer itself into the surface. And it was actually tested in something fairly hard on Earth in a simulated microgravity environment. And this thing can actually penetrate breeze block. So it can penetrate very, very hard material. Now, this is a diagram that actually shows what we saw on the day. This thing is about 330 millimeters long. And this shows how much of this stick that is supposed to be hammered into the surface is above the surface. So we want this number to decrease slowly from 330 to 0. That would indicate this thing is hammering into the surface. What we saw on the day was pretty much nothing. It was just wiggling about, and it was just, it was an initial progress, but then this thing just hammered and hammered and hammered and nothing happened. So it did not progress. And we concluded from this that the material must be rather hard. Otherwise, this very powerful hammer would have been able to hammer into the surface. So very hard material. And that's why you could see in the cartoon that Philae's little hammer also, there we go. Philae's hammer got bent a bit. So comet nuclei must be hard, not soft. That was our conclusion after the Rosetta mission. So in order to understand that, to reconcile this hardness and softness and so on, we also did some experiments in the lab, because obviously this is something that puzzles you as a scientist. Hang on a minute, why is a comet hard and soft at the same time? So we wanted to focus on the so-called dust mantle. As you could see in these images, there was also not much evidence of a dust mantle on top of a shiny white comet. So we investigated a fake comet in the laboratory. This time we didn't simulate Mars, but we simulated deep space. We put this thing into a vacuum chamber on our cold plate. This sample, by the way, has the same dimensions as the previous sample of the Martian ice sheet. So it's about 12 centimeters in diameter, 12 centimeters high. And we just mixed ice with a tiny bit of a dark material. We wanted something fluffy that is very dusty, very pristine. So we took carbon black, which is effectively soot. We also did some experiments with other materials, but that doesn't matter for now. And what we could see actually is that we could get the surface to become hard, and we could also see something like a dust mantle buildup. You need to bear in mind that this material initially is almost white. And after a while in vacuum, the surface becomes dark because the ice sublimates into vacuum. And then if you shine the sun at this stuff, the particles that actually form this dust layer and those that are still in the ice underneath are embedded in it, they sort of stick together and they form these dust aggregates that you can see here. And so these are, to the left, you can see the before, and to the right, you can see the after the solar irradiation of the sample. So we are basically creating a dust crust. And what you can also see is that between these black aggregates, you can still see the sort of white initial pristine material that has not sublimated yet. So that was one of the findings that we saw in our experiments. I'll show you this video just to give you an idea of what these experiments look like. Again, this is about, I think, something like 8 or 10 hours. It's a time lapse of what happens if we switch on the light. So we are in the vacuum chamber again in deep space, simulated deep space. It's quite cold. We've got some very porous, very soft ice. It's similar material to artificial snow on a ski slope, or very similar to sort of snow that has not consolidated. It's very fluffy, it's very soft, and it's mixed with only a minute amount of soot. Now we switch on the sun, and immediately you see that some of the dark stuff on the surface is blown away. So that's basically what is going to create the coma of our comet. And it'll end up in the dust tail if this was a real comet. And now we keep shining the sun at it. What we see is that whatever is left on the surface will then stick together and form larger and larger conglomerates. You can see that the ice disappears slowly. You can see the ice level sinking, and the black stuff remains on the surface as a black residue, forming a dust mantle and making the sample very dark in places and very bright in others. So this is our artificial comet. And the thing sticking out to the top right is actually one of our temperature sensors. Right, so that's our comet. It has evolved into something with a black crust. What was quite interesting was the formation of these clumps of black stuff. So these black clumps are up to 1 centimeter in size. And that is quite interesting because that also is something that resembles the observations of the Rosetta space missions. The dust detector detected some very fluffy, large aggregates. And what we created here are fluffy, large aggregates. It's only that our aggregates are chemically very simple. They're just carbon, but still they stick together in this environment. And they can't be glued together by anything because any water in there would just sublimate. So again, we've managed to simulate something that resembles one of the observations of the spacecraft. This is actually what these dusty aggregates look like. They're very fluffy. You can see that most of the stuff is void, and you've got these chains and fluffy chains of carbon atoms here. You can see this is an electron microscope picture that we took in our lab in Stirling. So if you now look at the ice underneath these dust things, we found that surprisingly there seems to be a certain amount of carbon that you need to add in order to get really, really hard ice. As I said before, this was soft material. It was more like snow than ice. But after a few hours of artificial sun in vacuum in these very cold conditions, we could actually get the substantial hardening of the material. And what we see in this graph is hardness on the horizontal axis versus depth inside the sample from the surface. That's the vertical axis. So at the top you've got the surface, and then 2, 4, 6, 8, and 10 centimeters below the surface, we're indicating the hardness of this sample. And you can see that at the top the sample is very soft. At the bottom it remains very soft. But you can see that for certain curves you can actually get a substantial hardening, and the colors represent the amount of soot we mixed into the ice. And I need to tell you that actually you've got this 0.2% carbon black in the ice, in the snow, in the artificial snow, giving you a very, very hard sample at a point below the surface. So we're able to reproduce the a very hard material below the surface just by adding carbon black to some snow, effectively, which was also rather surprising. And the 0.2% carbon black does not result in any sort of substantial darkening of the material. To the human eye, the stuff still looks white almost. It's just that that it seems to be enough material that absorbs sunlight to make this stuff actually really, really hard. Now, what we've seen here is that we were able to support some spacecraft observations. We could do sticky dust that was basically dry. We could form centimeter-sized flakes of dust with our soot or carbon black. We could create hardening of the ice just by shining the sun at the ice, which was quite soft. And we could also show that the hardness of the ice underneath the surface depends on how dirty the ice is. That means there's this dependence on the absorbing properties of the material underneath that is embedded in the ice. And we need to bear in mind that these materials, these flakes are just about 1 centimeter in size. Now, we've now visited a comet. Moving on from comets to more rocky stuff in the solar system, I'd like to give you a brief overview of something that was also quite interesting that was observed on asteroid Ryugu, which was a target of the Japanese mission called Hayabusa2. And then possibly I'll just mention briefly Mars Moon Phobos to get us back to Earth. Now, Why are asteroids so important in this context? We've talked about comets. Asteroids are in a warmer environment. The hang on. Asteroids are also thought to be quite pristine. In fact, these days we think that asteroids and comets belong to a similar group of bodies. They are part of a continuum of unconsolidated bodies in the solar system. And the Hayabusa mission was very interesting in that it, I'm still struggling with the controls here, was very interesting in that it was unprecedented in the complexity of the whole mission. The Hayabusa spacecraft was quite small compared to Rosetta. It was only like 600 kilos or so. I'll give you some data later. But it managed to carry out these very complex investigations of asteroid Ryugu, which was thought to be rather pristine. It was a C-type asteroid. That means it was carbon-rich. It was thought to be very primitive. And actually, it also took this fantastic selfie of itself. The whole mission, I mean, was very, very imaging heavy. There was lots of cameras on board and lots of pictures taken. And that was actually part of why this mission was such a success. Here's a picture of the asteroid Rugu close up. It was taken by a lander that was led by the same institute, DLR, the German Aerospace Agency in Berlin. And this picture was actually taken by a lander that the Japanese dropped onto the surface. And you can see that this material has, it looks rocky, but there's this, you can almost see that this is unconsolidated material. It looks fragile, fluffy, porous. And you want to touch it and just to basically to feel how crumbly it is. But unfortunately, we couldn't do that. Well, that is something we are trying to get together for the next mission that JAXA is flying. So we're hoping to collaborate on a new instrument that JAXA are flying to Mars Moon Phobos. So I'll tell you a bit more about the mission. So it was near Asteroid Rugu. Mass of the spacecraft was 600 kilos. The mission was launched in December 2014. And the main purpose of the mission was a sample return from this very primitive asteroid. The mission arrived at the asteroid in June 2018. Did about a year and a few months of observations. It departed on 13th of November 2019, and the sample was returned to Earth December last year. Mind you, at that point, most of the world was already in coronavirus lockdown. It was a major logistical effort for the Japanese colleagues actually to get a bunch of like several dozen researchers into an airplane, then into quarantine, and then to Australia, into the desert. So the target, Asteroid Rugu, is a bit less than a kilometer in size. Its semi-major axis is 1.2 astronomical units. Eccentricity 0.2, orbital period about 1.3 years, so pretty close to Earth. The mission had ion engine propulsion, which meant that the trajectory was quite complicated because there was never enough thrust actually to propel it anywhere directly, but still, got there in the end. And we've now got an extended mission because there's so much fuel left. Then there was this lander that I talked about that showed this image that gave us this close-up image. It had several rovers that just rolled about the surface. It also had a deployable camera that was a spacecraft with only a camera and an impactor. And it had several target markers on board to mark the location where it would then descend onto the asteroid surface to take a sample. So Heritage is the original Hayabusa mission, which was in a way, victory snatched from the jaws of defeat, in that the mission had been written off, but because of the bloody-minded and pig-headedness of some colleagues in mission control at JAXA, actually the whole thing made it back to Earth, which much delayed with only much less sample of material than hoped for, but still the mission had been written off before. So Hayabusa 1 was a fantastic success in these circumstances as well. So to give you an idea of the complexity of this mission, actually, here's an overview of the spacecraft with all the trimmings. So you've got several landers, you've got several cameras, a standalone camera, and so on. And they all did observations at the asteroid for more than a year. As I said, launch was 2014, arrival was in 2018, departure end of 2019, and sample return a year later. I'll show you some of the highlights from that mission. First of all, we did asteroid mapping, and then the lander was deployed, or several landers were deployed. Sampling was done, then impact experiment was made, and then another sample was taken in the impact crater to just sample the freshly exposed material. Ryugu's shape was determined. Density was quite low. Again, if you bear in mind that comets also have a low density, that tells us it must be a very porous body, 50% porosity. That means this thing is not held together by much. You know, most of what's inside is nothing. The rotational state was rather odd. Again, it's got a retrograde rotation, 7.6 hours rotation rate, and it must have evolved considerably because it's got this equatorial bulge. That means at some point it must have rotated a lot faster. Lander was deployed September to November 2019. There were 2 Japanese rovers, this one Franco-German lander. We got some close-up imagery, and we were able to in situ determine the thermal inertia. Now, thermal inertia tells you how quickly a material heats up if you shine the sun on it, and how quickly it cools down if you switch the sun off. And that is quite important because that tells you how fluffy or how crumbly a material is. You will find that, for instance, the thermal inertia of dust is very, very low, and the thermal inertia of a brick is very, very high. So if you measure the thermal inertia, you immediately know how porous, how fragile, how crumbly a material is. Sampling happened like this. There was basically a projectile that was shot into the surface, and then whatever was ejected was sampled by this massive horn that you can see in the center of this little video animation. As you can see, it was quite tricky because you've got this massive block to the left that you can see. You know, if the spacecraft had hit that, I wouldn't want to know what would have happened. The entire sampling process was done autonomously, by the way. So the spacecraft just dropped target markers and then descended all by itself. To give you a bit better view, there's this thing that has been produced by an amateur that gives you a different frame of reference and actually should give you a better way of orienting yourself in space. The spacecraft is descending, takes a sample, and misses that big boulder just by a few centimeters. So that was a stroke of luck. Overall, the spacecraft sampled 5.4 grams of material. Then there was the crater experiment. The mission deployed a impactor that basically just shot a massive block of copper into the surface. And because this is so dangerous to observe, it also deployed a camera. Then the spacecraft went to the other side of the asteroid. The projectile was fired, the camera observed, and then the spacecraft came back to sample the crater. So this is actually the ejector curtain that was produced by the impactor on the surface of the asteroid, Big Bang. And the spacecraft at this time was in a safe distance the other side of the asteroid, and then came back to sample material from this crater. You can actually see the crater in this blinking picture. You can see how this boulder in the center has moved to a different location. So the material that was then sampled had not been exposed to solar wind before, which was quite important. So 2 samples in the bag, and samples returned in December next year. So the question is, what next? I mean, I've told you a lot about the mission. What have we learned from this? And there has, of course, been a massive amount of science output so far already. We've got several papers. Look at them yourself. If you just search any database or search Science magazine for Hayabusa2, you will actually find some of the results published in an accessible way. A lot of the papers that have been published are actually open access. So it was a huge success, this mission. Now, I spent the past almost 1 hour talking about ice and dust in space, and how it is so fascinating. And you might want to know why it really matters. I mean, why are ice and dust so important? What's the relevance on Earth? And to illustrate that, I'm showing you our comet simulation experiments to the left, before and after, and the dirty ice, and a picture that was taken on Greenland by, I think, the Danish Polar Research Institute. And you can see that there are some similarities in that the ice on Greenland is no longer white either, and that is partly because of algae that are embedded in the ice, but you can also trace some of the black stuff in the ice back to China and some of the power plants there, some of the industry there, because what we mix into our ice, namely soot, that is produced and blown into the atmosphere in industrialized nations, and particularly in countries such as China, where there's still a lot of industrial production going on. We can trace the dust, the soot back to China on the northern hemisphere. In Antarctica, we can trace these contaminations in the ice back to desert sand in Chile, for instance. You can see dust from Chile making it all the way to Antarctica, contaminating the ice, lowering the albedo. That means the stuff melts earlier, which means that it is contributing to shrinking of ice sheets on Earth. Actually, see this nice little brook of meltwater on this ice sheet to the right in the picture underneath the helicopter. Now that is a scientific topic that is hugely relevant to Earth. What is it exactly that is driving the melt? Where does the water melt? What effect is the contamination having? And are there any ways we could change this? So, what we are doing in space research actually has direct relevance on Earth. Actually, we are collaborating with environmental scientists as well on this topic. However, to end on a much brighter note, I mean, my favorite form of ice in the solar system is in a cone in the sunshine and on Earth. And with that, I think I'll finish my presentation. So thank you very much for your attention.
All right, brilliant. Thank you so much. We're all virtually clapping, but obviously that wouldn't sound too good if all the sound was on. Brilliant. Okay, we'll check because we have two versions. Yes, I see more and more virtual clapping happening. We'll have questions coming in. If you don't mind, Alistair, feeding me questions from YouTube, if we get any. And as well, feel free to ask questions in the chat here on Zoom.
That's not a problem, Laura. I can provide you with any questions that come up on YouTube. I have a question myself, so I'll just go ahead with that. Thank you, Axel. That was a wonderful presentation. I really enjoyed the little the videos of the Rosetta mission. We had a talk about that a few months ago, maybe, and they were omitted, and we saw little snapshots from them, but they were very good. I guess I have a few questions, and maybe if we go all the way back to the Martian spider features, is the size of the feature, is that something that it grows and develops over time, and so the larger ones are, multiple seasons or cycles worth of melt, reform, and melt and reform, and that's what's growing them? And then I could imagine that if the dark particulates are coming out, then they're also exacerbating this problem and causing the effect to be more pronounced. Is that true? You're mute.
I don't know how to answer that question. The thing is, the dark particles that are coming out, they are usually deposited downwind. And then the whole ice sheet is thought to just disappear. And then again, you've got the buildup of the ice sheet again. And then the whole process happens again. An interesting question in that context actually is, I haven't followed this, whether anybody has come up with a reasonable explanation as to why these things happen at the same place always, same place again and again. I mean, why would it be at the same place that this thing is being produced? Because it is not necessarily, or the ice layer on top of these things is not necessarily always there. I mean, we've got locations where the ice disappears, and then basically we've got the buildup of the ice over the season again. Is that a sort of inconclusive answer to your question?
That's absolutely fine. I'm perfectly happy with that. Thank you.
Great. Thanks, Alistair. We've got a question from Karen. Is it possible that some comets are hard and some are soft?
Short answer, yes. It is possible because we know that comets are diverse, just as asteroids are diverse. We now know that that comets can stem from different regions in the solar system. We know that they have seen different stages of processing. So yes, I mean, definitely, some comets can be soft, some can be hard, some can be hard and soft at the same time. That brings up the whole question of what is a comet? What classifies a comet? And for instance, we've seen gas activity from asteroids, like Ceres, for instance. And that means, okay, is anything that is outgassing a comet or not? Similarly, is anything that is stuck together by ice, is that a comet or not? So yes.
Great, thank you. I've got a question, so I'll just ask it. See, in the simulation that you showed where the ice is melting and eventually it kind of looks like Oreo ice cream and then it turns kind of gray, for instance, the last phase where it's like really small speckles of that, would that be like the final phase of an asteroid or a comet before it kind of splits? Or does that have nothing to do with the lifespan of one of these objects?
I would say but because the timescales are very different. You're addressing two important points here. Firstly, I mean, you've just mentioned the Oreo ice cream, and I'll bring that up as an analogy in my next talk because I like that. And secondly, the timescales are very different. Our simulations just last, like, I think the maximum was like 16 or 18 hours in this case. And within these 16 or 18 hours, we got like a mantle of like 5 centimeters of water ice to just sublimate, disappear, and we had these particles on top. Now, if you carry on with that process indefinitely, you eventually will have got rid of all the ice, and all that remains is the hard stuff or the non-volatile stuff. And depending on all the other material that you've got, and you can not only have, for instance, soot or carbon black, but you can also have silicates, you can have silicate dust, you can have rocks, entire rocks of stuff. So effectively, what I suspect what will be happening is that you would gradually transform what is actually a comet into an asteroid, because all the volatile stuff just disappears. Now, whether that actually works in reality is an interesting question, because it might be that once the ice glue is gone, the whole thing will just disintegrate, just, as you mentioned, like the Shoemaker-Levy 9 comet, and just it end up with meteor showers, effectively.
All right, thank you. I might have another question coming from this later, but I see there's a couple questions coming in. One of them from Craig. Do asteroids outgas like comet nuclei? If so, what's the difference between them, if any?
Yeah, that is, I got myself into trouble mentioning that. There are a few asteroids of which we know that there has been gas activity. We have observed outgassing from several asteroids. I don't remember them all. And that the first asteroid to be observed outgassing, that was, I think, in the late 1990s or possibly early 2000s. And similar to exoplanets, there have been more and more being observed. And that was actually a milestone in our understanding of the origin and evolution of the solar system, because that led us to realize that comets and asteroids are not two entirely different bodies. They are sort of part of a continuum, because we've now also found many, many more asteroids. As the observing techniques got better, we found, for instance, Trojan asteroids. We now realize that asteroids are not only limited to the asteroid belt, but we can find them in various places in the solar system, and all the way further out. So that basically means that there is this continuum now between that includes both comets and asteroids. And the distinction of comet and asteroid is being made by whether it approaches the sun and whether it then builds up a coma. So you've got a coma and possibly a tail, and that's what makes a comet. And if it doesn't do that, it is an asteroid. But that doesn't mean a comet is necessarily that much different from a comet in terms of composition. I think, yeah, I hope that answered the question.
All right, thank you. Great. I hope that satisfied you, Craig. All right, we've got a question from YouTube, from Simon. Can your experiments give insights into how an asteroid or comet behaves when it collides with Earth? How high it explodes and how intensely, for example?
Actually, no, I don't think so, because there are many other parameters that actually influence how a comet or asteroid interacts with Earth. I can share a bit of the information that we gained from the space missions in that context as well. We know from the low thermal inertia that Hayabusa has measured that a lot of the material that makes up Asteroid Rugu, at least the surface, would probably not survive intact if it entered the Earth's atmosphere. The interesting conclusion we can draw from that is that because hang on a minute. The interesting conclusion we can draw from that is that we now also need to revise our understanding or our picture of meteorites and their connection to asteroids, because the Ryugu asteroid was assumed to be sort of one of the potential parent bodies of a class of very primitive meteorites, the carbonaceous chondrites we find on Earth. Actually, the one that came down in Gloucestershire, was it, like a couple of weeks ago? That was one of these very, very rare meteorites. Now, the Ryugu was supposed to be one of the potential target bodies of this class of meteorites. Now, the material that we have investigated on the surface was too fluffy to survive atmospheric entry. That means we have to now go back and say, okay, well, this cannot be the parent body of these meteorites. It has to be an entirely different class of body. Similarly, now I'm getting to the question. Now similarly, our experiments can tell us a lot about cohesion, but I think an impacting body that depends on the overall mass of the body and then on the cohesion of the body. And the cohesion then depends on well, how much volatiles you've got sticking the stuff together, how brittle the material itself is. So if you do lots of these experiments, many, many, many more, with lots of different materials, we will possibly be able to say something about the amount of energy that will be released if something enters Earth. But what we can say so far is only that we need to revise our ideas of the amount of energy that is being released, and we need to revise our ideas of the stuff that actually hits Earth, because what we thought up until the Hayabusa mission seems to have been wrong. Full stop. Did that answer the question?
We'll see. Guess we'll get a feedback eventually. It does seem quite exciting when we hear that everything we assumed was wrong as well. Element of mystery.
It's just very, very common with space missions. Actually, whenever you fly a space mission, to answer a question, you end up with a host of new questions, because you will find that in a way everything as you assumed beforehand was turned upside down. I mean, it started with the Giotto mission to Halley, when all of a sudden this comet turned out to be black rather than white, and everybody thought these things looked like snowballs. So there you go.
Nice, very mysterious indeed. All right, we've got another question from Alistair and another question from YouTube. I'm gonna ask you the YouTube one before. Sorry, Alistair. From Achio53. Sorry about the pronunciation. Care to comment? Oh, that was what I was gonna ask actually. Care to comment on, and then I don't really know how to pronounce this.
Oumuamua.
Yeah, how would you say it?
Oumuamua. I'm
Okay,
not
right.
doing that right,
So,
but
yeah, the comet that had been, well, what seemed to be a very mysterious comet observed from Hawaii. So do you have any comments on this particular topic?
I wasn't involved in the observations, and I have nothing to add. I think, some people even thought that, theoretically it could be anything. It could be like an alien spacecraft. I think that was one of the craziest ideas. But, there is nothing to prove that you're wrong, unfortunately. So.
Actually, very, very recently, some information came out, and I shared that on Facebook recently on the Facebook page. And basically, I think they think it's from a Pluto-like planet. It's made of ice nitrogen. I think that was the information. And it would be from a Pluto-like, well, Pluto's not a planet, but like object from another solar system. And it's because of its constituents, like being nitrogen ice, that it doesn't have a tail like you would see on an object like this normally. So this isn't very, I've vulgarized the language so much, but that's why I understood from it. So, all right. Another question from Craig. No, Alistair, I'll let you ask your question before. Go ahead.
thank you, Laura. And I'll just start by saying that Simon, who asked the question about how the asteroids, comets would behave if they collided with Earth, says that you have answered his question, and it was very much more. Your answer was very much more interesting than his original question. So his thanks. I wanted to ask a little bit about the black material, the centimeter-sized black material that's forming when you're doing the sublimation of the gas inside the vacuum chambers. You were saying that depending on the concentration of the carbon, that material is hard. Is it hard enough that it's stronger than the breeze block breaking hammer on the Philae lander?
I mean, the hard material is the ice, yeah? I mean, the fluffy stuff that remains fluffy. The material that we hardened actually was effectively artificial snow. The 160 megapascals, what we produced in the lab was not, 160 megapascals is not as hard as the stuff that Rosetta measured. I mean, we measured 160 kilopascals maximum hardness. Rosetta measured something that must have been several megapascals, so an order of magnitude more. However, and this is again one of the limitations of our experiments, we had the sun shine at that thing for about, I think, 8 to 12 hours. I don't remember the number. You have the sun shining at 67p for 4.5 billion years, a large part of that far away from the sun, but a significant part of that very close to the sun. Now, I would assume that with that much time, you can harden pretty much anything. So what you need is an energy source. You need some vapor flow of the gas, and off you go. You can sinter something. You can sinter it as hard as you like. If you model it, actually, a colleague has done some numerical simulations, and he can model something that is rock hard up to, I think, several tens of meters deep.
And sorry, I'm just going to tack on another little thing onto that. Does that mean that you would suggest that asteroids, or sorry, more specifically, meteorites and such like, Are you saying that those could possibly be things that have been in orbit around the sun, getting closer to it, hardening up before they enter the atmosphere, or are we saying that's a totally separate formation channel?
That's a different story, because the comet, I mean, all the hardened ice eventually will disappear. It will just burn off, and the thing will fracture, and effectively what will be left is just the rocky residue of this body, so of this comet. And that is, the ice is unlikely to be what is holding the asteroids in the asteroid belt together, because again, you know, they've had millions of years, and assuming that the orbits are sort of, you know, halfway stable, they've had millions of years to outgas all that stuff, and a lot of the asteroids actually do not require anything holding them together. If you look at Asteroid Rugu, you can actually see how the shape of the surface has evolved. I mean, the whole shape reflects something that is spinning very, very quickly, with the rubble being redistributed towards the equator, and then something must have changed the spin state. And on asteroid Bennu, if you followed the OSIRIS-REx mission, you could actually follow the material being ejected into space by the rapid spinning of the asteroid. So I think you need to distinguish between the ice component, which is something that's holding comets together, and the asteroids, which are in which ice might play a role. At least we can deduce that from the outgassing of some of these objects, but it doesn't play the role it's playing in comets.
Okay, thank you very much.
All right, that was cheeky. 2 questions in one. Wow. We've got a question from Craig once again. Is the fluffy material on the surfaces more like cauliflower or soap bubbles in consistency?
The fluffy material in our experiments, that was, it's neither nor. It's cellular material. It's very similar to fresh snow, like snowflakes. You've got very fragile, very sort of, I would say, almost fractal material, where these grains actually have contact, very small contact areas, and it's almost like a mixture between like a network of stuff, like a net and some granular material. The closest thing I could think of is actually snow. However, when you talk about, you mentioned cauliflower, and cauliflower was something that was suggested in relation to the close-up picture of the Asteroid Bugle surface taken by the mascot lander, because colleagues said this looked like cauliflower. And that is a really, really interesting observation in its own right, because that not only suggests that the material is very, very fragmented, it also suggests that possibly there has been some sort of flaking of the surface happening. So possibly the surface has lost part of its material and it has flaked off, and possibly there are lots of little micro cracks and fissures that actually run through the material vertically. So this cauliflower analogy is quite important in this context, in the context of Hayabusa2.
All right, that is a really good question, actually. I thought Craig was just hungry, but that is really interesting. All right, another YouTube question from Alexander. Is there any realistic chance the combination of rock and ice in the comet could lead to potential nutrients for life?
Very good question. Nutrients. I didn't understand that. Nutrients for life, or what is nutrients?
Yeah, potential nutrients for life. I guess like the recipe for life. Yeah.
Well, nutrients for a life form, or that's a very good question, and I don't know the correct answer to that. There are some suggestions that some of the very, very early building blocks of life, such as some organic material, such as amino acids, were formed in these very, very cold environments. You need, in order to form the initial building blocks of life, you need an energy source. And the question is, where does the energy come from? Because the components or the ingredients for this recipe you've got. I mean, you've got organic material, or at least you've got carbon. You've got silicates. You've got all sort of other gunk. You might even have some iron, which possibly is a very, very strong catalyst. And the question is, where does the energy come from to form these early carbon compounds? The question is so good that actually we are currently writing a research proposal on it, believe it or not.
I honestly didn't expect that, actually. That's really interesting. But it does bring me back. The Open University you did work with, they've also been analyzing this bit of from a comet or a meteorite that had a little crystal of water in it, liquid water. I forgot the name of the speaker we had, actually, who had analyzed this bit of meteorite. Do you know what I'm talking about?
Richard Greenwood.
No, it was a woman, but maybe he was part of the team. But I know that I think it was a meteorite that landed maybe in the 90s, and only now we could analyze it. And it had a little blue crystal in it, which contained water and a bubble of air in it. Mm-hmm. Actually, I'll research that. I was frantically looking online trying to find the name of the person, so I'll add on this afterwards. All right, I'll just move on to the next question from Billy. I joined the Planet for Zooniverse project to map out spiders and fans on the Martian South Pole. Can you tell me how these two types of events are related in both size and terrain shape?
Say again, which two events? Can you repeat that?
So spiders and fans on the Martian South Pole.
Okay. Spiders, how these two things are related? Well, spiders are the remnants or are the signatures of the process in the soil. Spiders dig in, and the material that is then ejected into the atmosphere, basically, if that stuff is deposited, that can form a sort of a fan-like feature. And if you get a change in wind direction, you can also see that actually sometimes you get these dust aprons like in various directions on the surface. So I think in a way that hopefully clarifies how these two are related. I don't know whether you necessarily need a spider to form a fan, but I don't think so.
All right, thank you. And yeah, Zooniverse is really good. If anyone doesn't know what it is, you can contribute in scientific research by analyzing images mostly and data, and is a really good way to participate in astronomy, even if you don't have a degree. And I found the person, it's Dr. Queenie Chan, and it was organic matter and water that had been found from the asteroid Itokawa.
Okay.
But yeah, but basically organic matter had been found in it. So I think it kind of relates to the question of the elements for life that had been asked, possibly. All right, another question from John. Is there any chemical similarity between the hardening of ice with small amounts of carbon and the hardening of iron with small amounts of carbon to give steel, or is it just a coincidence?
That, I'm afraid, is a coincidence, because for us the carbon acts as an absorber for solar energy. It effectively transforms, or it converts electromagnetic radiation into heat. That's what carbon does for us in the ice. And that's how the ice hardens. Whereas in making steel, actually, there is a chemical reaction that's going on. So there are two different matters. In making steel, if you heat the whole thing. You know.
All right, thank you. I'll ask another question, actually. When you mentioned ice glue, did you mean the kind of like glues due to the nature of the water molecules, I guess? Right, how does that work?
Well, I mean, water molecules we can basically bind together because of the crystal structure of ice. I mean, you know, they like to stick the hydrogen to where the oxygen is, and that's how you can basically find these hexagonal structures. And ice glue, what I basically meant by that is you've got, you know, water molecules between grains of other stuff. And now, if you freeze the water molecules, then obviously you will have a solid binding together two pieces, you know, two particles. That's all I meant by that. Nothing really elaborate. And I you know,
Okay.
Glue was probably the wrong word. Yeah.
No, it's cool. I just wanted to make clear it's just due to the nature of ice, basically. And I guess it's not completely answered, but for most of these objects, do you think that the components of it are homogeneous throughout the object generally, or is it completely different? Okay.
In fact, we deduce too much from what we observe on the surface, I believe, because we, for instance, looking at 67P, the Rosetta comet, it seems like that what we've seen on the surface, that there is very, very little ice. I mean, I think the spectrometer data suggests that an ice content of like just a few percent, and that is vastly different from what we thought about, for instance, Halley's comet. So no, I don't think these bodies are homogeneous. They are, in fact, very heterogeneous, and just the bilobate shape of 67P even has been interpreted as indicating that this used to be two separate objects.
Oh, okay.
In 67P, did I show it? Yeah, I mean, you also saw it in the cartoon, the historically accurate cartoon. You know, it looks a bit like a rubber duck, and it's quite possible that the head and the body of the rubber duck are made of two different types of material. Or used to be two different bodies. And inside, we don't even know what's going on inside because the radar sounding experiment didn't quite work, unfortunately, because the lander was in the wrong spot and facing the wrong way. But what's going on inside, we have very, very little idea about. But no, I mean, these things are not homogeneous. I mean, they are too pristine to be homogeneous. They haven't undergone the mixing that for instance, is happening in larger bodies.
All right. Okay. And these this rubber duck-shaped object, what kind of lifespan would it have, and how would it eventually disintegrate? I guess if it disintegrates.
I'm pretty sure somebody will have done a master's or PhD thesis on this, but I don't know.
All right. Well, food for thought. I will look it up. Well, I see we've exhausted the questions, I think, unless there are some questions coming from YouTube, Alistair. Yeah, Alistair asks the lifespan of a rubber duck. Yes. It's quite really.
No, I think that's all the questions, Laura.
Yeah. Thank you very much. Thank you for your input. And thank you, Axel, for your endurance throughout with the questions and everything. This was so interesting. And I will post some information related to your talk for sure. Afterwards, yes, an outpour of positive comments coming in on top of this. Alistair is clapping virtually. Thank you very much. yeah, so thank you for that. I think this concludes our talk until the next one next month, and do come along whilst you can, everybody, because this summer is the end of astronomy until September when it gets dark again. So yeah, thank you very much.
Thank you very much, and for your patience.
Great. All right. And Billy asks, actually, how's the sunshine in Kiruna?
Oh, I mean, you know, we are approaching the vernal equinox.